Hi everyone, welcome back. This is Earth and Space Science 101, and we're still in Unit 1 of this class. This is Lecture 4 on the Earth's interior. Now, this is going to be, again, directly, in line with everything that we've been talking about so far. Tectonics. Tectonics creates geologic structures. Geologic structures like faults create earthquakes, and earthquakes give us a tool for understanding the Earth's interior. And that's what we're going to be doing today, looking at seismic waves and their utility in understanding the Earth's interior and what we can understand from the Earth's interior based on this information. Now, so this doesn't seem like, for a civilization that went to the moon, like this should be a real problem, understanding the interior of our own planet. Given what we know about Jupiter, what we know about the moon, what we know about the sun, or even distant solar systems and galaxies, it doesn't seem like it should be that big a deal to try to figure out what's going on in the interior of our own planet. But the problem is we can't access it directly. As much as we might want to and as much as we might try, we've never even been to the mantle. Our earthly experience is limited to the crust of our planet, just that thin layer analogous to being on the skin of the apple. And we've never gotten into the actual meat of the apple or the seeds or any part of its interior at all. So any analysis of the Earth's interior has to be done indirectly. We cannot access it directly. Now, we have certainly tried. We've drilled very, very deep drill holes. Most of the longest drill holes that have ever been drilled have been in pursuit of oil and natural gas, but those are seldom directly vertical. Those often go in various patterns, kind of drilling sideways for a while and then back off in the other direction for a while. And the actual deepest drill hole is attempting to get down to the mantle, but like I said, it's never actually gotten all the way down to the mantle before. So we have to look at the Earth's interior indirectly. Now, the best way that we have to be able to do this is through understanding seismic waves. Most of these seismic waves are generated through earthquakes, but some of these can actually be generated artificially. So whether the waves are created artificially through something like, some small contained explosion, even something as simple as a hammer on a metal plate, or through an actual earthquake, the waves are the same, and the waves tell us about the Earth's interior. Now, when these seismic body waves, and remember, the seismic body waves include the P wave, that stands for primary wave. That's the one that compresses and dilates the material, that's essentially analogous to a sound wave. When those P waves and the S waves, those are the shearing waves, the ones that can't travel through liquid or gas. Whenever those waves travel away from the focus of an earthquake or some controlled experiment on the ground surface that's going to produce these earthquakes, once they travel outwards, their speed is going to change depending on what material they're moving through. Another way of saying speed, and have it be a little bit more scientific, is to talk about velocity. Velocity is just the vector version of speed. Speed just tells you, hey, I'm going this fast. Velocity is speed with a direction. So typically we use the word velocity instead of speed, and that gives us an idea of what direction these waves are moving in addition to how fast they're moving. That velocity of the P wave and the S wave depends on a few factors. It depends on what type of material they're traveling through, even to the distinction of different types of rocks having different velocities. It depends on the phase of the material, whether it's a solid, liquid, gas. P waves typically travel slower through liquids than they do solids, slower through gases than liquids. That's why the speed of sound is so much slower than the speed of those same P waves moving through a solid. And they are going to, that seismic wave velocity is going to depend on the strength of the material. So something that is a fairly weak material, like an unconsolidated sand in the subsurface, has a much slower overall seismic wave speed than that same sand if it's well cemented, if it's a sandstone rather than loose unconsolidated sand. So to give you the idea of some of these different types of velocities, how fast these waves are traveling through different material, I've constructed a little table for you, just of some of the most important materials and their correlating seismic waves. There's obviously air, so that's the composition of the Earth's atmosphere, mainly nitrogen, a little bit of oxygen, tiny little bit of other stuff like argon and carbon dioxide. It has a P wave velocity of 0.3 kilometers per second, or that's about 0.2 miles per second. This could also be interpreted as this is the speed of sound. The sound that's coming from me and going to you is traveling in that particular speed because these are P waves traveling through the Earth's atmosphere. Now, it's a lot easier to break the sound barrier than it would to be able to break the speed in which these same waves are moving through liquids or solids, which, like I said, can be 10, even 20 times faster, depending on the density of the material involved. These same waves, these same P waves travel a lot faster through liquids than they do air, and P waves can travel through both gas, liquid, and solid, where again, S waves can only travel through solids. So that's why I don't have a reading for the seismic wave velocity of the S wave moving through air or water. Now, I have 3 different types of rocks, and I've put these in a sequence dependent upon their density. These rocks have different compositions, and the individual elements that make up these minerals and make up the rocks are going to have different overall densities, being some of these atoms are going to be arranged closer than others, and some are going to be a little bit further away. So sandstone is less dense than granite. Granite is less dense than basalt. And the other reason I picked out these 3 materials is because they give you a pretty good sort of general overall idea of some of the most common types of rocks that make up the Earth's crust, and similar to some of the rocks that make up the Earth's mantle. Sandstone is a rock that makes up a fairly large percentage of the Earth's surface. Granite is a rock that composes most of the overall composition of the continents, especially in the deeper layers of the continental crust. And basalt is the most common rock in the oceanic crust. So sandstone has about half the seismic wave velocity of basalt, a little less than half of granite. And again, that makes sense. As you have higher density material, the waves can travel faster through that material because the particles of substance that make up that material, the atoms and molecules that make up that material, they're closer packed in a denser rock. And it makes those waves easier to move. In something like the air, these particles are much, much further spaced, so that means that the waves travel slower. Now, the S wave velocities are obviously a much, much lower. They travel at overall about roughly half or sometimes less than half of the speed of the P waves, but they do move through eventually. Again, the reason for this is because of that shearing motion of these waves. The wave vibration is perpendicular, or in the opposite direction of the direction that the waves are actually propagating through the material. So while these waves are traveling through one particular type of rock, they're able to maintain a steady speed. So let's say, to kind of try this out, let's say that the entire interior of the Earth was only made up of one type of rock. If it was a completely uniform big marble in space, and it was only made up of basalt, then seismic waves stemming from an earthquake near the Earth's surface would be able to travel through the entirety of the Earth's interior, all the way through, maintaining that constant speed, and come back out the other side. And the fact that they never changed their speed would tell us about the uniformity of the Earth's interior. Now, they don't actually do that. The seismic waves don't do that at all. They speed up as they move through the Earth's interior, moving faster and faster and faster. And that tells us that the interior of the Earth is getting more and more and more dense as these waves travel through. They also don't speed up and slow down gradually. They speed up and slow down really abruptly at particular boundaries between one type of rock and the next. So all this tells us that the interior of the Earth is a lot less uniform than we would like to think. It's actually very diverse. It's very interesting, and it undergoes all of these changes from the outside in. And those are the kind of changes that we're going to look at today. So when these seismic waves interact with a boundary between two different types of material, the response is going to be that these waves are going to either slow down or speed up, depending on the density of the material underneath. In some cases, when you have a very low angle wave and a very, very sharp boundary between two very different types of material, most of the waves, especially those traveling at a low angle, will actually just reflect off of that boundary. And that tells us a lot of information. You could put different seismic recording devices all along the ground surface and pick up these waves as they reflect off the boundary and then bounce back up to the surface. And it allows us to image this boundary. It's very, very similar to how we use X-rays in order to understand the bone structure in somebody's body. So we don't actually have to cut them open to see whether or not their bones are broken. We can use X-rays, and we can determine this indirectly. So instead of X-rays for the Earth's interior, we use seismic waves. And these seismic wave reflections, reflecting off a particular boundary, can tell us that that boundary is indeed sharp. So this boundary between layer A and layer B in this picture might be the boundary between a fairly loose, unconsolidated sandstone with relatively low seismic velocities to a layer of basalt that has obviously much higher overall seismic wave velocities. So due to the low angle of the wave and the highly reflective nature of the boundary being between two very different types of material, those waves bounce back up to the surface. And it allows us to say, here's the boundary. Here's where the interior of the Earth changes. Another thing that may happen when these waves interact with a boundary between two different types of material is if the boundary is a little less sharp. If instead of being between sandstone and basalt, it might be between granite and basalt, which have more similar seismic wave velocities. The waves might not reflect off of that boundary. The waves might continue to move through that boundary and down to lower levels, deeper interior layers of the Earth, but they might change their angle. So whenever the same phenomena happens with light on water, it causes this distortion of anything that might be underneath the water. I think everybody in their lives has taken a stick or a pencil, maybe something like that, and put it in some water. And when you look at it, it looks like the pencil is actually bent. But it's an optical illusion due to the light refracting off of that boundary between the air and the water and causing this apparent distortion of the pencil. It's about the refractive index of water. So the same thing effectively happens in the interior of the Earth. In the interior of the Earth, those waves, especially if they're relatively at a higher angle and the boundary isn't that sharp, those waves will continue to move through the boundary. They might just change their angle a little bit. Now, if you have a boundary where you have a higher density material below the boundary, those waves will kind of continue to change their angle in such a way that they'll eventually reflect back up to the surface. If you have a stranger kind of boundary between, like, let's say, higher density material below, higher seismic wave velocities, and lower seismic wave velocities and lower densities below, you might have a change in angle that makes those angled waves a little bit steeper so that they would then continue to move into the Earth's interior. But regardless of what happens, the waves continue to move through the boundary, and that's the point. They refract, like light refracting off of the surface of the water, and not reflection. So essentially, I like to compare these layers within the Earth where something changes, a boundary between two different types of rocks in the Earth's interior. I like to kind of compare that to the boundary between water and air a lot. Because if you stand at a particular angle to a surface of water, it's easy to see your reflection in that water. So some of the light is actually reflecting off of the surface. But if you might change your angle a little bit and maybe look directly above the surface of the water, you can look through the top top of the water and you can see underneath. It's just going to cause a distortion in your view of things under the water, and that's refraction. So reflection and refraction are essentially the two things possible that may occur when a wave interacts with a boundary between two different materials in the Earth's interior. We know that those boundaries are present because seismic wave velocities do change as they travel through the Earth. We just don't know exactly where they are until we study it further. So we can use all of these earthquakes that have occurred, close to like 100 years worth of earthquakes, every single one allowing us to get a little bit of new information about local geology and worldwide geology, and they can allow us to kind of paint a little bit of a picture of the Earth's interior. The way that we're going to explore the Earth today is from the outside going inward, with a concentration on this idea that our understanding of the Earth's interior is based off of these seismic waves. So we're going to look at what happens with the seismic waves and then paint a little picture of what the interior of the Earth is like at all of these different points. So we're going to start with the Earth's crust, because we're working from our way outside and going inward. Even the Earth's crust hasn't been fully explored in a much more direct sense. You know, it's particularly the oceanic crust is very hard to explore directly. It's much easier to use seismic waves to give us a more vivid picture of what the overall thickness of the oceanic crust looks like, rather than drilling, which is much more expensive, especially if you're doing this principally to explore the crust in that area. So what seismic waves would tell us generally about the Earth's crust is that it's much thinner and far, far more dense under the oceans, that oceanic crust has a much higher density, higher seismic wave velocity than the continental crust. The continental crust, while it's often thicker and thickest under mountain belts, is often a lot less dense, meaning those seismic waves are going to travel much slower through the Earth's crust. So this is information that we talked about already in the first lecture in this class, the basic distinction between the granitic continental crust and the basaltic oceanic crust. But now we have the very, very important point of why is it like this? Why do we know that the continents are more light and buoyant than the oceanic crust? And the principal reason for that, for the why, is the behavior of these seismic waves. Now, things get really interesting when we get down to the base of the crust, and this is worldwide. This isn't specific to one particular location on the Earth's crust or in the interior of the Earth. Worldwide, there is a very, very sharp boundary between very different types of rock at the bottom of the crust and the beginning of the mantle. This is such a highly reflective boundary that the vast majority of all the seismic waves created by all the earthquakes are going to reflect right off the surface of this boundary. And it's only going to be the highest angle and most high magnitude earthquake events creating the strongest waves that are going to be able to actually penetrate through this boundary and to be able to explore the interior of the Earth. The geologists that first went about understanding the base of the crust and the beginning of the mantle has a very, very difficult, long last name. His last name is Mohorovich, so it became the Mohorovich discontinuity. This is this very, very reflective boundary that marks the base of the crust and the beginning of the mantle. Generations of geologists have found that very difficult and cumbersome to pronounce, so colloquially it's more just known as the Moho. We call the base of the crust and the beginning of the mantle the Moho. And what you need to take away from this is that it's a very sharp boundary where things change dramatically. The mantle is composed of far, far more dense rock than the makeup of all the crust, even the oceanic crust. So in terms of density, we're going to go from the continental crust, which is comparatively like a pillow. It's very, very light, very, very low density, to the thin oceanic crust, which is more dense than the than the continental crust, and then the mantle, which is still composed of rock, but it's a very, very dense rock. It means the particles are far, far closer together, and the makeup of these rocks is a lot of much heavier elements, stuff like a lot of iron and magnesium and calcium, as opposed to particularly the continents, which have a higher abundance of silica and some other elements present that are not as heavy, things like sodium and potassium. So at the base of the crust, we have the Moho. Most of these waves reflect off that boundary. We know it's a big, sharp boundary, and that's why the Earth is subdivided into crust and mantle. If this big, sharp boundary didn't occur, we would just basically call the whole rocky part of the Earth something like that entire thing is just all mantle or all crust. But it's not. It's a big, sharp boundary. So we are going to go into now the next big subdivision of the Earth's interior, which is the mantle. Now, in the mantle, the seismic wave velocities are much, much higher than even in the oceanic crust, getting up to close to, in some cases, like 11 or 12 kilometers per second. So we know that this is a very, very dense rock. And because both the P and the S waves can travel through most of the mantle, with some exceptions to that rule, we know that most of the mantle is actually in a solid state. Now, remember, the reason why we know this is because the S waves are incapable of traveling through liquid. So if there is an isolated pocket of magma in the mantle, some hot spot that's stemming upwards towards the surface to create a rift and to create a divergent plate boundary, then the S waves aren't going to be able to travel through that part. But they do travel through most of the mantle. Now, these seismic wave velocities aren't quite high enough to suggest that the mantle is actually composed of metal. It still makes more sense for it to have a rocky composition, more silicon and oxygen, calcium, iron, that kind of thing, than to just be pure metal. The other really, really interesting thing that all of this tells us about the mantle is that it's not uniform. And again, that's kind of what we like to think going into this study, that the Earth's crust is going to be uniform and heterogeneous all the way through, and that the mantle is going to be uniform all the way through, and then you've got this big spinning metal ball in the middle, and that's the core. That's kind of the 8th grade level Earth science interpretation, that there's just this big blob of the interior of the Earth that's all the same. The seismic wave velocities would argue with that idea and say that there are several major changes that are going on throughout the mantle because the seismic wave velocities are going to continue to increase. So what I'm going to show you now in this next image is a graph overlaid onto a cutout of the Earth's interior that tells you what these seismic waves are doing from the surface all the way in. So it includes the crust, the lithosphere. That first tiny little orange layer at the top is the asthenosphere, where because of the ductile nature, you have a little bit of a slowdown in the seismic wave velocities. And then as you get into the mantle proper, so the lower parts of the mantle and all the rest of that long extents of the mantle going all the way down to the liquid outer core, which is that kind of bright mustardy yellow color, you can see that the seismic wave velocities don't just gradually increase over time. They do so in this sort of stair-step motion. So every time you see one of those little stair steps, like at 400 kilometers of depth and 670 kilometers of depth, in both the S waves and the P waves, whenever you see that, it marks the change in the assembly of the minerals that are present within those rocks. What happens is, at a certain temperature and pressure, those minerals are forced to assume a more high-pressure form. The individual atoms making up those minerals assemble themselves in an even tighter configuration. And then that marks an abrupt increase in the seismic wave velocities because all of a sudden the rock has become more dense. And then a few hundred kilometers lower, it does it again and again and again. And so this gets marked in both the S waves and the P waves. So at various depths within the mantle, you continue to have minerals, you continue to have rocks, and they continue to assume a more and more and more dense overall construction. Most diamonds are actually sourced from not the crust, but the upper part of the mantle, where it's possible to actually take carbon and to configure it into a high pressure form. The low pressure version of carbon, the one that's actually stable over long periods of time on the Earth's surface, is graphite. It's what makes up pencil lead. But the high pressure version of carbon makes diamond, and those diamonds are originally sourced from the mantle. They're only brought up to the surface through really, really explosive volcanic eruptions. Which are incredibly rare, haven't actually happened in millions of years. And so then those diamonds are actually brought up to the surface. So you could kind of think of the diamond as an example of a mineral that's forming in some of these very high temperature, high pressure environments. So in order to kind of get a little bit of a better idea of what's going on with these high pressure minerals and what's going on throughout the mantle in general, we're going to take a little field trip. But unlike in past cases, we're going to come back from that field trip and we're going to finish out the lecture in this situation. So please enjoy it. So, in today's lecture, I spent a lot of time talking about indirect observations of the Earth's interior and why that's important and why that allows us to know what we do know about the mantle and about the state of the core. So I thought it might make a nice change for our field trip to talk about a direct observation of the Earth's interior through the world's deepest borehole. So this is the world's deepest man-made drilling platform. It's called the Kola Super Deep Borehole, and it's located on the border between Russia and Norway. This is actually drilled by the Soviet Union starting in 1970, and they drilled all the way up into the year 1989. And they finally had to stop drilling because temperatures in the deeper part of the crust were so hot that they couldn't continue drilling. They were basically sort of melting all of their equipment trying to drill any deeper than they had already drilled. But even though they didn't reach their original objective, which was to try to get as far through the continental crust as possible and potentially even all the way down to the mantle, they still revealed a lot of really useful information to us about this area of the world, this area called the Baltic Shield, which is the name of the continental crust in this area. They revealed that it's actually a lot thicker than was originally anticipated, and what was originally thought to be this transition between granitic rock that would have lower overall seismic wave velocities to basalt underneath it. It was actually a transition between the granite to a metamorphosed version of that granite. So a completely unexpected rock type emerged in the deeper part of this borehole. So the borehole is actually 40,000 feet deep. It makes it still the deepest borehole anywhere in the world, but not still the longest. It was actually outpaced as the longest borehole by oil and gas wells, one in particular. But the reason why it's still the deepest is because these oil and gas wells, while they do tend to be quite long, they will sometimes run, instead of directly vertical, they'll run horizontal for a little while. So they twist and turn in this objective to try to get to as much of the oil and gas as possible. All right, so I hope you enjoyed that little outing. Now we're going to pick up right where we left off, which was we had gone through the entire mantle. We're now at the bottom of the mantle. And what that image that we had just been looking at also shows us that in addition to seismic wave velocities continuing to increase throughout the mantle, at the base of the mantle, they do exactly the opposite of what we would expect them to do. If the Earth is increasing in density, as we understand it to be, all the way through the Earth's interior, we'd expect the seismic wave velocities to keep increasing along with it. And at the base of the mantle, the seismic wave velocities drop off significantly. They go back to the same sort of velocities that we had at the surface. So this is really, really weird. This marks one of the strangest areas in the Earth's interior. And unfortunately, it's one of the areas that we can explore the least because we're getting really, really close to the center of the Earth at this point. We're now at the bottom of the mantle and the beginning of the core. So at the core mantle boundary, you have almost sort of the opposite set of circumstances that you had at the crust mantle boundary, where you have a gradual boundary between the base of the mantle and the beginning of the core. You have a nice little solid line, like it's been drawn in with Sharpie at the base of the crust and the beginning of the mantle. But at the bottom of the mantle, it's just this kind of huge fuzzy area where weird things are happening. And most notably, the seismic wave velocities decrease significantly. So we call this huge area at the base of the mantle and the beginning of the core, we give it its own sort of specific name, and that's D double prime. A geologist in the early 20th century named Bullen came up with this way of understanding the Earth's interior by designating all of these geologic layers with a letter. But the only one that ever really stuck was this weird area at the base of the mantle called D double prime. So he would have A, B, C, D, and so on, and then he'd subdivide D into D prime, D double prime. D double prime is the one that's strange, and so the name sort of stuck. So contrary to what you may have learned prior to this class, it's really not just crust, mantle, core. It's crust, mantle, D double prime, and core. Because this D double prime is really a very unique layer in its own right. It's actually a thicker overall layer than the entire thickness of the crust. And it's one that's marked by all of these changes that might be really sort of expected in an area that subdivides two very, very different compositional and structural layers, the mantle and the core. So this D double prime layer in the accompanied ultra low velocity zone, or ULVZ, could be happening because of one of two reasons, or more likely because of both of these two reasons. They're not mutually exclusive. One could very easily influence the other. The first possible reason why seismic wave velocities decrease so suddenly right there at the base of the mantle and in D double prime is because of the presence of this hot metallic core could possibly be melting the overlying rocks. If they're melting, this means this rock is going from a solid to a liquid state. And as we found out already, when you change the phase of a material, it's going to change the speed in which the seismic waves progress through that material, and also the ability of the S waves to travel through it at all. And both of these things certainly happen at D double prime. The secondary reason why this is happening, and again, it's very logical that these could both be happening, is because of a chemical reaction between the metallic core and the overlying rocky mantle. So you certainly have elements like magnesium and iron already present within the rocks of the lower mantle, but you could be forming some very, very weird minerals that are only really present in the lower mantle because of the abundance of iron and nickel in the core. So you could have a reaction between those, forming a whole new set of minerals that can really only ever be found in the high temperature, high pressure environment at the base of the mantle in D double prime. So, So for both of these reasons, seismic wave velocities decrease really suddenly, and really it's just a very, very strange overall layer. It's a gradual layer defined by this gradual change between the mainly solid rocky mantle and the liquid outer core that's mainly metallic in composition. So now we're to the core, and you'd like to kind of think of it as the heart of the Earth, but this is actually a very, very large overall section of the Earth. This is a substantial part of the overall composition of the Earth is just this core, and it's all iron and nickel. So it's not just Earth that we think has a large iron and nickel core. We think that all the terrestrial planets, so Mercury, Venus, Mars, we think they all have a large metal core, just like Earth does. Unlike some, not all of those other planets I just mentioned, our core is in at least still a partially liquid state. We think Mars may have at some point had a core that was in a partially melted state like ours, like the outer core was actually in a liquid state, but there's no evidence that Mars has an overall magnetic field. So it's very unlikely that its core is actually still in a molten state. And that lack of a magnetic field is the primary theory as to why Mars doesn't have liquid water on the surface anymore or a very thick atmosphere. It essentially is what makes Mars essentially uninhabitable, is the lack of a liquid outer core. Now, it's an important point to remember what makes a planet have a liquid outer core, or to have really any liquid inside the interior at all. To take something like a metal, iron and nickel, and to force it into a liquid state, it takes incredibly high temperatures and pressures. So, and mainly temperatures. So it's, again, the fact that the interior of the Earth is hot is what's driving geology on Earth. And in this case, what's driving the magnetic field. So I'm getting ahead of myself a little bit. The core is in a partially liquid state, and it's iron and nickel in composition. We don't actually have any direct samples of the makeup of the core, but you can look at the Earth's mass as a whole and try to sort of back calculate the composition of the core with the known quantities, which are the composition of the mantle and the crust. And the thing that most likely fits is something that has an iron and nickel composition. It also matches up with analytical compositions of meteorites, which we think have some of those same building blocks that once constructed our planets. And they are typically very high in both iron and nickel as well. So you have two components to the core, the liquid outer core of our planet and the solid inner core of our planet. And what we have in the outer core versus the inner core is this really delicate, almost beautiful interplay between the effects of temperature and pressure. If there was no increase in pressure exposed to any of these components of the Earth's interior as you move inward, then the entire core would actually be in a liquid state. But what happens about halfway through the core is that the effect of temperature forcing all of this metal into a liquid state becomes outweighed by the continued increase in pressure. Pressure takes over and forces that liquid back into a solid state. So the very, very center of our planet is a solid ball of iron and nickel, surrounded by an ocean or a sea of liquid iron and nickel. Now, there are two major pieces of evidence for the fact that the outer core is in a liquid state. And the most obvious one, the one that you really can't possibly argue with, is this fact that the S waves can't travel through the liquid outer core of our planet. And because they can't travel through, they leave a shadow of S waves on the other side of our planet. So maybe a better way of thinking about it would be this. If you have a very, very big catastrophic earthquake, a high Richter magnitude earthquake happening on one point on our planet, on one side of the world, it creates waves that can actually travel all the way through the Earth's interior. The P waves actually do travel all the way through the Earth's interior and come out the other side. But the S waves travel through the Earth's interior until they get to the outer core, and then they just disappear. And then those S waves can't reach the other side of the planet, thus leaving sort of the equivalent of a shadow when you're dealing with the nature of light. In this case, it's an S wave shadow zone. So the S wave shadow zone is our first line of evidence that the outer core is in a liquid state. The one that we've known about for a far longer period of time, however, is the presence of the Earth's magnetic field. The Earth's magnetic field is one of the most interesting and dynamic things that makes our planet a really cool, habitable planet. It's happening as a result of the convection of the liquid iron outer core of the Earth. And if the interior of the Earth were ever to freeze out, which it will do eventually, maybe 2 billion years from now, when it eventually completely cools off and the outer core solidifies, the Earth's magnetic field will no longer continue to regenerate itself. But as long as the interior of the Earth is hot, then that outer core, all that metal, is constantly in motion because it's undergoing convection. So the hot metal rises, the cool metal sinks back down towards the inner core, and it continues to move. As long as you have a moving metal in the presence of a pre-existing magnetic field, like something like the magnetic field from the sun, then you can continue to produce your own magnetic field. And this one is worldwide. So it's really strange to think about, but our entire planet is one huge magnet. And this huge magnet is the reason why things like compasses point north. It's the reason why birds know which direction to fly, because they have the equivalent of tiny little compasses in their brains. It's the reason why we have the auroras, this delicate interplay between charged particles and the gas right outside the magnetic field, closer to the poles. All of these happen as a result of the magnetic field. So what I want to show you next is a cool little a clip of video that shows you this relationship between electrical currents and the magnetic field. So I hope you enjoy it.
Scientists have a theory about how the core generates the magnetic field. It's based on the close relationship of magnetism to electricity. In particular, the fact that electric currents create magnetic fields.
Now, there's no electric current going through the coil to start with. The iron filings just go down like pepper in a pan, but if I turn on the electric current, then you can see the iron filings line up with the magnetic field that's produced by the current in this electric coil. So it's really currents inside the Earth's liquid metal core that we think gives rise to the magnetic field.
But what gives rise to the electric currents? The answer to that is where things get complicated. Scientists believe that just as the electric currents produce the magnetic field, so the magnetic field produces the electric currents. The key is that the liquid metal in the core is in constant motion.
If you take a moving conductor in the presence of a magnetic field, currents get set up inside the conductor.
In the Earth, the moving conductor is 1 billion trillion tons of molten iron. But the effect can be seen in a simple loop of wire connected only to a meter which measures electric currents.
If I move this conductor in the presence of the Earth's magnetic field, then that gives rise to currents. Once you have currents, those give rise to magnetic fields. So it's kind of a curious loop that gets set up in the Earth's core. A little bit of magnetic field couples into the motion of the liquid, gives rise to currents flowing in the core. Those currents cause more magnetic field, which cause more currents, more magnetic field. So it's kind of a feedback loop that can cause the magnetic field to just rise.
So hopefully that gave you a little bit of a better idea of how the magnetic field works and how it's a self-sustaining dynamo, how it continues to work over time. So the magnetic field currently is running essentially sort of out of the South Pole and into the North Pole. So that's it basically just meaning that a compass would point towards the geographic North Pole as opposed to the geographic South Pole. Now, I say this because it hasn't always actually been that way. Magnetic reversals are very, very common. And when a reversal occurs, it means that the field would run in the opposite direction. South would become north and north would become south. The field would be running out of the geographic North Pole and into the geographic South Pole. Now, we still don't really have a very good handle on exactly why this occurs, but we do know that reversals are often heralded by a weakening of the worldwide magnetic field. Instead of having one direction of polarity, you really almost have several directions of polarity where the field's running in and out of the equator and in and out of maybe 30 degrees or 40 degrees latitude. So you don't really have this nice sort of organized magnetic field that runs adjacent to the rotation axis of Earth. And then the field will eventually reassert itself, but in the opposite direction of polarity than when it started. Now, I can tell you that on average, these reversals happen maybe once every 200,000 years, and we have evidence that they have occurred essentially throughout recorded geologic history. But they don't really happen with any definite periodicity to them. So it's not like they can only happen to every 200,000 years. Sometimes it'll be 1,000,000 years between these reversals, and sometimes it would be, only 1,000 years. In our case, it's been 713,000 years since the last magnetic reversal. So we're, in a sense, sort of overdue for another one, but it certainly doesn't mean it's going to happen tomorrow or even during our lifetimes at all. These magnetic reversals give us very, very important evidence for plate tectonics. And so we're going to be using these in the next lecture. In our next lecture, we're going to be talking about the plate tectonics theory, the origin of the plate tectonics theory, a little bit more of sort of the advanced science in plate tectonics, and we'll eventually start talking about mountain belts as well. So I hope you have enjoyed this one. I hope you enjoyed next one. So until I see you again, keep rocking.